Hello everyone, today we'll be looking at Lab 4. Now the biggest issue we face with our lab is that we have our spin-locked threads from Lab 3. These are threads that need a resource and don't have it. This leads them to spin, do nothing in a while loop, for example, for the entire amount of time that the RTOS has given them. However, when you're programming at a system level, it's important to consider all cases and systems that are either non-deterministic or very hard to determine guaranteed states for. In our case, if a thread takes the semaphore finished and gives the semaphore back, there is a chance that the other threads are asleep and never take control of the semaphore, and we will context switch all the way back around to thread 1, and it will retake the semaphore, and therefore it will never ever give it back up. In order to get around these issues, we want to use what are called blocking schemes. Instead of doing nothing after a thread is scheduled, we simply do not schedule that thread at all. Thus, we want to implement some way to tell our scheduler what the thread is asleep via fields in our TCP struct, as we see here. In better usage of our time, we may also want to switch to an X thread forcibly when we sleep a thread, because we know that that thread is very, very likely not to get the semaphore in its runtime, so we don't want to waste time spinning around doing nothing at all. This is the basis for our scheduling. Yes, so that's part 1. The next part is what we call priority systems. So sometimes we want different threads to run over other threads. For example, with an audio system or perhaps a screen display system, we really want that to run strictly at 30 FPS, or that to sample at a certain rate, or an interrupt to take precedence over another one. We'll touch on interrupts in a second here, and we need a priority system for that, so that other threads may override other ones, which is useful. Moving on to part B, we need to enable data transfer between threads. It is important that we understand that threads do share address spaces, unlike processes. For those of you who have taken operating systems, they don't share stacks, however, which is what we covered in Lab 3. This is useful because it lets us refer to pieces of memory in a global fashion. However, there is an issue when we have incomplete read and write cycles that happen on these items. We introduce what's called the FIFO, first in first out queue. For those of you that have any experience in cross-clock domain design in FPGAs or ASICs, you may already be familiar with them. Their main useful aspect here is that they enable what we call asynchronous transmission. Basically, we do not have very strict requirements on the timing for writing and reading to them. We just know that there may be data in it, and there may be data not in it, so that we can put more data into it. In our case, one thread may add to the FIFO, write to the FIFO, a few entries in its context window. Reading for a sensor, for example, it may update the sensor a few times, and then we context switch and we go to another thread, and it may read from the FIFO, take from the FIFO, processing the data from the sensor, and pushing it to something that may display that data later on. The important fact lies in that our entries are complete inside of a FIFO, so we are guaranteeing that there are not incomplete read or writes sitting in our FIFO, which is good. You implement a basic ring buffer for this, which basically has a few fields inside of its struct, pointer to the head and tail of the buffer. This pointer is maybe a realistic pointer, or it may be a metaphorical pointer, in the sense that we write to the stuff on the head, aka the position, then the buffer that the head points to. So if we have 16 spaces, then our head may point to position 4, and our tail may point elsewhere. We will write to the head, and then we want to read from the tail. So we will pull data out of it, and then we will move the tail accordingly. It is pretty simple, I think. The next part for part C is dynamic threading, aperiodic and periodic threads. So we have different types of threads, actually. Our normal threads run in our little context window, maybe 1 millisecond that we have set. However, there are issues where we cannot strictly guarantee that it's going to be 1 millisecond, or it is very difficult to guarantee this. So we will implement what are called periodic and aperiodic threads. For example, our aperiodic threads with interrupts. So we might need to use an interrupt for something. How do we use an interrupt when we may not be polling for one directly? The entire point of an interrupt is that it's polled for on chip instead of in software. We need to tell our thread that it can run based off of these interrupt threads, which is what's called an aperiodic event. So you will have to go in and implement those to send a signal to run based off of those. The other important part of what we call periodic threads, these are threads that only run ever so often. Again, because we cannot guarantee that we have a set 1 millisecond between each of our normal threads, there are certain threads that we need to run at 1 millisecond, and we don't need to run any faster than that. For example, we have a display that we want to run at 30 FPS. We don't need to render it at 40 FPS because that's not what we want, and it would perhaps not be of any use because our engine behind it may not supply data consistent with 30 frames per second, so there's no reason to render it at 40 frames per second. Therefore, we do not want to use processing time on this. So we will use what are called periodic threads. Our periodic threads are quite simple in the fact that they will use a timer interrupt perhaps, and they will run every so often. Again, screens are a good example of them. Speakers are also useful in the sense that we may want to sample at a specific rate. We cannot guarantee that rate strictly out of basic 1 millisecond context switches, but we can guarantee it with hardware timers. Parts D and E are rather simple. We will just be interfacing a little bit with the other things we have on the board. And part E is putting it all together. We have given you most of the code that you require for part E in terms of the threads. This is a little program that renders cubes on your screen based off of a camera. It is important that you use this because it has been designed such that your RTOS must be implemented and implemented well, that this will function. Otherwise, we have no quick way of determining that your RTOS is functioning correctly. And our little bonus points, they're a significant amount because I feel that changing the shape rendered by the camera can be difficult at times, to say the least. That is it, everyone. Good luck.